Hello students, today we are going to discuss about rocket equation. When we talk about rocket, it is mainly about the vehicles. These are the vehicles which pushes some certain kind of materials or some objects into the orbit of Earth. Okay, see, if you consider this is the Earth, okay, and the Earth is having a motion around its axis like this. Now you see, above the Earth there may be some kind of orbit. Okay, this is the orbit. Okay, so there may be an orbit like this also. Okay, there are so many orbits. There may be another orbit like this. So you can see that this is a low height orbit, lower orbit, this is a higher orbit. So for this case also we may have some orbits like this. Okay, there are so many different kinds of orbits that you can define for Earth. So suppose the rockets are basically the vehicles which carries different kinds of satellites. Satellites, you know, satellites are basically carrying some machines or detectors which observes into the outer space. They also help us in communication, and different other applications are there for the satellite. So this is a vehicle, and it is basically rocket is a vehicle. Now you see, rocket basically carries a payload. Okay, and say it is a payload. Payload means you might have seen that whenever ISRO is launching some rockets, they have some payloads. They have their own detectors or objects to be placed in an orbit. Payloads means if somebody is some other country or some other organization is giving some satellite or some object to be placed on behalf of them, okay, into the Earth's orbit. So payload or any kind of satellite, whatever you want to place into the Earth's orbit. So this is detachable. And other is the body of the rocket. Fine, as a body of the rocket. And now you see that when the rocket will be moving, means moving into the from Earth's surface into this area. Okay, sorry, this is a lower Earth orbit, as I told you already. Suppose the rocket is leaving from Earth's surface to reach a certain orbit. So you know that this is doing, all these things are being done against what? Gravity, isn't it? Earth has a strong gravitational pull. So the rocket is moving towards the orbit, towards its destination or designated orbit against the pull of gravitational pull of Earth. So it is not easy for the rocket. It will have to do some work against this gravity. That means it will have to use some kind of energy to reach that orbit. And for example, you can see that if you want to reach this lower orbit, as I have shown you, this is the lower orbit. Okay, for this low orbit, the rocket has to get accelerated, or has to attain a velocity of around 17,000 miles per hour. Okay, miles per hour to reach that particular you can say lower Earth orbit. This is the velocity that it has to attain. So it is a very high velocity. That means it will, to achieve this velocity, the rocket will require a lot of energy. This energy is basically obtained from the fuel that it will be carrying. Okay, so you can say that the rocket is basically the payload. Okay, then the body of the rocket, okay, its own body, and then what is there? Then it is fuel. Okay, so we will call it P plus B plus F. Okay, so now then that means to attain this much of velocity, the dependence will be totally on how much fuel the rocket is basically carrying. Okay, so there is a fuel inside the rocket also. Okay, this is a fuel. Okay, this is the body of the rocket. Okay, I'm just giving an idea. Okay, don't take this diagram very seriously. This is just a representation. Okay, so what rocket equation basically does? Okay, for a certain, this payload will not be always a constant mass. Okay, the payload may vary. The mass of the payload Now depending upon, now for a certain mass of the payload, there will be a certain mass of fuel, okay, the fuel that you need. That means the rocket equation, this gives you how much fuel you will be requiring to place a certain payload of a certain mass. Okay, so for a particular mass of a payload, there will be a particular mass of the fuel. So rocket equation basically gives you how much fuel will be required to place a particular payload of a certain mass into the low Earth orbit or any other orbit of the of Earth. Now this derivation of the rocket equation is basically divided into three parts. Okay, the first part we will derive the expression for velocity of the rocket, okay, inside Earth's atmosphere. Fine. Second, we will derive the velocity of the rocket in space, means outside Earth's atmosphere. Okay. And at last, we will derive the rocket equation. Fine. So rocket equation will need the expressions for both this and this. Then we will combine and we will find the rocket equation. Now the thing is that in an exam you can expect that you may be asked to find out the velocity of the rocket inside Earth's atmosphere. You may be asked to find the velocity of the rocket outside the Earth's atmosphere. So if you are asked this one, you will do up to this. If you are asked this one, you will have to do up to this, both. Okay, and if you are asked this one, then you will have to do all the three. Okay, it depends. So you will have to check while answering the question in exam. So again I am repeating, if you are asked to find out the velocity of the rocket inside Earth's atmosphere, you will do up to this. If you are asked to derive the velocity of the atmosphere in space or outside the Earth's atmosphere, then you will have to do both. Okay, if you are asked to derive the rocket equation as a whole, you will have to do all this. Okay, so that's the thing. Now let us start with the velocity of the rocket inside Earth's atmosphere. So let me tell you one thing. Suppose it's the Earth's surface. Okay, I'm just showing in a regional basis. So the rocket is launched like this. You might have seen that how rockets are launched, is it? So you might have seen that some huge amount of gas is coming out, fumes are coming out whenever the rocket is moving. Okay, up in the upward direction. So you see, it will move and move and move, and after some time, what will happen? The Earth's atmosphere will be the Earth's atmosphere is only extended up to certain distance, okay, up to certain height. Okay, after that it will be the space. There won't be any kind of atmosphere. So this is the Earth's atmosphere and this is the space, and say the orbit is somewhere here. Are you getting? The orbit is not inside Earth's atmosphere. Earth's atmosphere is up to this only. Okay, but beyond that it is space, and the orbit is somewhere here. Okay, so when the rocket is moving from Earth's atmosphere, it is actually passing through two phases. One is within the Earth's atmosphere. That means it will get the gravity effect of Earth, and then it will be beyond Earth's atmosphere. Then it will be space. There will not be any gravitational effect. Means there won't be any effect of gravity of Earth on the motion of the rocket. So we are going to divide this. We will have to do the derivation in two different stages. So first of all, if you consider the movement of this particular thing, then you will see that when the rocket is moving upward, there are two things acting on it. Okay, definitely one thing, that is downward. Okay, downward. What is that? This is a weight, isn't it? The weight of the rocket. Okay, as a whole, whatever weight is there, fine. And another is called upwards. Okay, that is nothing but called thrust. I will tell you what is thrust. So we have two factors. Both of them are acting in the opposite direction. You might have seen that when the rocket is moving upward, there are fumes coming out, is it? Okay, so rocket basically works in the principle that is Newton's third law of motion. Every action has an equal and opposite reaction. Okay, because you know that the Earth has to move in both space and also within Earth's atmosphere. So basically the thrust is basically resulting from the propulsion of fuel, okay, burning of fuel. Because thrust, you know that it is a reactional force. Thrust is also a force, but it is a reactional force. What is that reaction? When it will be, the fuel will be burnt and there will be propulsion in this direction. What will happen? This is an action, okay. So this action, according to Newton's third law, there will be an equal and opposite reaction, okay. This reaction will push the rocket in the upward direction, okay. The same principle is valid in case of in the space also. I will give you an example of a balloon, okay. Suppose you have a balloon, okay. So it is tied now properly. Now if you release this thread and slowly what will happen? The air will be moving in this direction, but at the same time the balloon will move in this direction, isn't it? If you slowly release the air from the balloon, what will happen? The balloon will move in the opposite direction. So this is the action and this is the reaction. Fine. So in place of balloon, now we have a rocket, okay, carrying lots of weight, and we have a fuel. So in place of air, we have fuel now, and the fuel is in huge amount, so that burning of the fuel can give you enough of propulsion so that it can move in the opposite direction, okay. So the thrust is basically is a reactional force which is coming from it is a reactional force and is coming from the propulsional of the fuel. So here the fuel is burned and the propulsion is direction, so it's in action, and this is the reaction. The reaction is nothing but what? This is the thrust, okay. So that means because of this reactional force, that is called a thrust, the what you can say that the particular rocket is moving in the upward direction. Now and what principle the rocket is using for moving? That Newton's third law of motion. That means every action has a equal and opposite reaction, because you see within Earth it has an environment to push against, is it? But whatever happens in space also it is using the same principle of action and reaction. This principle of action and reaction doesn't depend whether there is a medium or not, okay. So if I ask you that within the surface of Earth, within Earth's atmosphere, what is the resultant force acting on the what I can say, the resultant force acting on this particular on the rocket? So you know that the rocket is moving, is it? The resultant force is what? Upward force is winning, is it? So upward force is what? Thrust minus what? Weight. I'm getting. So as we have discussed in last video, that the resultant force acting on the rocket is thrust upward minus weight, okay. So you know that the formula for force is nothing but mass into acceleration. M is the mass of the rocket, okay. I'm telling that as a whole, the total mass of the rocket includes P plus B plus F, okay. And then thrust, leave it as it is, I will describe it later on. And weight, again mass into acceleration due to gravity. Now you see that thrust is nothing but reactional force, isn't it? What is the formula for mass force? M into A, okay. So in our case this A is different because of reactional force that I am describing. So you know that M in acceleration is nothing but dv dt, isn't it? So now in this case you see the velocity V is if we consider thrust is basically resultant because of the propulsion of the fuel, is it, in the downward direction, okay. So that means here this V is basically this velocity is basically nothing but the velocity of ejection of the fuel, okay, how much fuel is getting ejected. So I will write it as du dt, okay. But interestingly you will see that we can write it like this, ddt of m into u. You see u is basically constant, the velocity of ejection of the fuel will remain constant, okay. But only thing that is going to, if the fuel is burnt, what will happen? The mass will reduce, isn't it? The mass is going to reduce. The mass is not going to be constant. As in the normal cases, mass is basically constant. That is why we keep it outside. But in this case, the situation is different. The mass is changing. The fuel is getting burnt. fuel is getting burnt means the mass will never be the constant. So here in our case, the total mass is nothing but capital M into U. Okay, so we are writing is that U is constant and dm dt. Okay, so U is not going to change much. The biggest change will happen in the mass of the rocket. Okay, so which also includes the mass of the fuel. Okay, it includes in the mass of the fuel. So overall the formula for thrust will be equal to U into dm dt, where U is the velocity of ejection of the fuel, and this is the rate of decrease in the mass of the rocket. Okay, or you can say that rate of mass ejection. Okay, so that means what we are going to write here, m into a thrust I will write as dm dt minus mg. Okay, so m is common everywhere, so I will write it u by m dm dt g. Fine. Again, a is nothing but dv dt. Okay, now a is the acceleration of the rocket here, so it is equal to dv dt, where v is the velocity of the rocket. Remember that v is the velocity of the rocket, but u is the velocity of ejection of the rocket. Okay, so it will be u by capital M dm. So dv dt means acceleration means change in velocity of the rocket. V is the velocity of the rocket at that particular instant. U by m dm dt g. So I can further write it as dv equal to u by capital M dm minus g into dt. Okay, but you can see that this dm is basically reducing. Okay, mass is decreasing with respect to time. So if I consider dm, it will actually be negative. Okay, it is always reducing, it's not positive. So what I am going to put here is a minus sign. So if I want to integrate it, it will be dv minus u by capital M dm integration g dt integration. Now you can see that let us consider that initial velocity of the rocket is v and final velocity is v naught and final velocity is v. Here mass is going from this much to initial to last, so capital M initial. Okay, and this is M final. I will tell you about it in detail. Now you can say that M is changing, isn't it? So why we are keeping it outside, we will also keep it inside. So v naught to v dv equal to minus u is kept outside, it will be dm by m. Okay, so m initial. Okay, m initial means what is that? Payload plus body plus fuel, is it? And this is m final, is it? That I will call it empty. Why empty? Because all the fuel has been emptied, so it will be only the payload plus the body. Okay, fuel has been emptied, so m final is nothing but m final I'm writing is as m empty. M empty means it doesn't have any, it is means it is no fuel, all the fuel has been burnt, and by the time it has reached the orbit. Okay, by the time it has reached the orbit, the mass will be empty. Okay, so here as if you are considering for a time t, see this is this all to be done. So 0 to t gt. So suppose that the rocket has not yet reached the orbit. Okay, not reached orbit, so then also you can call it empty because it has already emptied, means most of the fuel has been emptied. Okay, so while it is moving, the mass will be emptied. So if you consider at any other time other than 0, we will always see that the fuel has reduced. Okay, payload and this body will remain constant, but fuel has reduced. That is why we are naming it empty. Instead of m final, we are writing as m empty. You can write as m final also, it's not a problem. You can write m empty also, but m empty means that if it has reached the orbit, the fuel is 0, but if it is in the middle of the way, it has not yet reached the orbit, the fuel has decreased but not fully. Okay, so continuing from the last, it is v naught to v dv minus u, it is m initial to m empty. I already discussed. You can write m empty or m final also, it's up to you. Dm by m minus g dt 0 to t. Okay, so that means I will write it as v minus v naught. Okay, and it is u, so it is ln, is it? Means log e, log base e. Okay, log base e. So ln, it will be ln m, fine, and it will go from m initial to m empty minus g into t. Okay, so minus u, so it can write as ln m empty minus ln m initial, okay, minus gt, plus u ln, so I will write, it will be like m empty by m initial, fine, minus gt. So you can write m ln, I can write m initial, because if I negative means it is minus 1, so it will be inverted, so m empty. I hope you can understand this step. This is minus, this logarithm, is it? So this minus can go there as minus 1, 2 power minus 1. 2 power minus 1 means it will be reversed. Okay, that's g into t. So v minus v naught. So v is basically equal to v naught plus u ln m initial by m empty minus gt. So this is the velocity of a rocket at any instant t inside the Earth's atmosphere. Okay, so this is a very important derivation. So this is the first stage we have completed, and next we will start the second stage. Now look into the second stage of the derivation. So now we are going to find out the velocity of the rocket in outside Earth's atmosphere, that means in space. So as you remember, it was force is equal to thrust minus weight, isn't it? Now interestingly, it will be weightless in space, isn't it? Because g is equal to 0. So what remains? F equal to, it is ma, and thrust is u dm dt, isn't it? So again, dm dt is negative, as we have already discussed, so I will mark it as minus. So m is so I will keep it a, so it will be u by capital M dm dt. So it is nothing but dv dt minus u and d u by capital M dm dt. So dv will be equal to u dm by m. Okay, let us integrate in a similar way, and this time is again it is going from m initial to m empty. Okay, so you know that it will be v minus v naught is equal to u ln m empty by m final, initial. I'm not showing each and every step. You should check in the note and also do by yourself. If you have any doubt, you can ask me. So it is simply mathematics, nothing to do with physics. So it is v naught, and this initial I will keep in the up and in numerator, and it is in the denominator, so there will be minus, so it will be positive. So ln u ln m initial by m empty. Okay, fine. So what is the beauty? This is outside Earth's atmosphere. So what is the beauty of this equation? That means in space, even you are not with the rocket by yourself, they are not there, you can calculate the velocity of the rocket at a certain instant of time. How? Because when you have the rocket in the ground, you will have a parameters of the you know how much is the initial mass carried by the rocket. Obviously you know that, and you know that at what rate the mass is being ejected. Okay, so you know how much fuel will remain in the rocket after a certain amount of time, is it? So you know initial, obviously you know, and you know that mass empty, how much fuel has been emptied. Okay, so if you know these two values, you can easily determine what is at what particular velocity the rocket is moving in the space right now. Okay, this is the mathematics used to calculate the velocity of a rocket at a certain instant of time. Now after this we will try to derive the exact rocket equation. Okay, you should know what are the uses of the equation. First equation we have already derived, and this is the second equation. Now let us discuss about the main rocket equation, how to derive this. So this is basically based on a principle of conservation of momentum. Okay, so imagine that suppose that we have this is Earth, okay, and the rocket is leaving Earth. Fine. So at a certain instant of time, the mass of the rocket is capital M. When I say capital M, it includes the fuel mass, then payload mass, and body of the rocket. Okay, and suppose that it is moving with a velocity v in this direction. Okay, now at the same time the rocket is ejecting. Okay, it is ejecting what? Fuel. Okay, so fuel in the opposite direction. Let us assume that the velocity of the fuel is u. Now imagine that consider that this is a velocity u of the fuel with respect to the rocket. Okay, just consider this thing. This is a velocity of the rocket with respect to Earth. U is the velocity of the fuel with respect to the rocket, because the fuel is coming out of the rocket. Okay, now this is the u velocity and it is towards the Earth, and this is a velocity with respect to Earth, but it is towards away from the Earth. Okay, now assume that within time dt. Okay, let us consider a small interval of time dt. Okay, during that time the mass has changed by dm. Okay, obviously you know that the mass is the fuel is getting burned. The total mass of the rocket will definitely keep on changing, means it will decreasing. Decreasing means what? The velocity will keep on increasing. Fine. So velocity is changed. Velocity has changed by a value dv. Fine. And see, v is the velocity of this particular rocket at a particular instant of time, and this is with respect to Earth. U is the velocity of the fuel expelled. Okay, expelled from this rocket with respect to v. Now if I ask you what is the velocity of this fuel with respect to Earth, then it will be v minus u. Okay, so this is the velocity of fuel ejected with respect to Earth. Okay, u is the velocity of the fuel ejected with respect to the rocket. Understand the concept. Okay, now let us apply the concept of conservation of momentum. So by the law of conservation of momentum, you know that the momentum should always remain constant, is it? So initially what happened? The total mass of the rocket is m and velocity is v. At that time mass has not changed, v has not changed. Okay, so you know that then after dt time what happened? Mass has changed by dm and velocity has changed by dv. Okay, so I'm not writing increase or decrease, I'm just writing as change. Can you understand? So initially the mass of the system is m and velocity is this. So this is a total momentum of the system rocket and the system of rocket. Now the fuel is getting separated, it is getting burnt, so it is expelled. So what will happen? The mass of the rocket has changed, okay, and velocity of the rocket has also changed, okay, but this is for the rocket, okay. Next, since mass has changed here for the rocket, so this change in mass is nothing but if the mass has decreased, so this is the mass of nothing but the fuel ejected. So dm, whatever is getting ejected, see here we have two systems, this is a system and this is initially this is the whole total single system, later on the fuel got ejected, okay. So now it is a different system, this is a different system. For this system it is m plus dm into v plus dv plus, now we need to write for the fuel, okay. So dm into, now what is the velocity? So see, this is v plus dv, this is the velocity of the rocket away from the earth with velocity of the rocket with respect to earth, okay, but it is in this direction, and velocity of the fuel with respect to earth is nothing but v minus u. But the thing is, it is not in this direction, it is in this direction. So the overall momentum contribution by the fuel will be what? Negative, okay, because this is with respect to earth away from earth, this is with respect to earth but towards the earth, so there is a opposite sign, fine. Now if I do the calculation, m into v plus m into dv plus v into dm plus dm dv, v into dm minus minus plus u into dm, okay. So it is mv gets cancelled, vdm gets cancelled. So dm is a small number, dv is also a small number, so multiplication of two small number is again a small number, so it can be neglected. So m dv plus u dm equal to 0. Now what we can do? M dv is equal to u dm, so dv equal to u by m dm. Alright, so integrating v dv, see what I said initially that it was v and later it was v plus dv, so it will be v plus dv is equal to minus u integration dm by m initial, and this is m empty. So we have stopped in the last video right here. So you see v from v to v plus dv, that is the integration minus u m initial to m empty. Now again I would like to say that this m empty, what is m empty and what is m initial? Okay, m initial means there is a weight of the payload, then the body of the satellite, and then the fuel, okay. And then m empty means obviously payload will be there, okay, body will be there, okay, and fuel means the fuel has got reduced, okay. How much fuel had got, so there is a difference between these two things will remain constant, the only thing that will change is the fuel, okay. So if you take subtraction, means if you minus m initial and from m empty from m initial, what you will get, how much fuel has been burnt till now, okay, during the now if the satellite has reached its orbit, then it will be what? 0. This thing will be 0, that means all the fuel has been exhausted, they have been burnt. Now you see here what happens. Now this is so m empty doesn't mean that everything is empty, it depends upon the time, okay. So if you have reached the orbit, then obviously it is empty, it has only the payload and the body. So let us integrate this, so it will be equal to del v equal to minus u ln, it will be m empty by m initial, right. So it will be e ln m initial by mt. So that is del v will be equal to u into ln m initial by mmt. Now u is the velocity of ejection of the fuel that you can set in the rocket by yourself manually or by the program. Where m initial, it is a well known that how much weight is carried by the rocket at initial stage. All of you know what you need to do. You need to add the mass of payload, the body, and the fuel that you are adding. So that is the initial. And the mmt means after a certain interval of time, suppose del t, how much fuel has been exhausted. Okay, because if you know at what speed the fuel is getting ejected, basically it is constant, as I already mentioned. It is around 4000 meter per second. It is ejected at this velocity. Okay, so velocity of ejection of the fuel is 4000 meter per second, and this is constant. Okay, so if you know this u, you will know at time del t how much fuel has been ejected. So you can understand how much is the empty. Just subtract that value from this total, then you will get what is mmt. Okay, so by knowing this value, you will understand what is del v. Del v means how much velocity is to be attained by the rocket. You know that when the rocket starts, okay, when the rocket starts, its velocity is equal to what? 0. And I told you that to reach up to that orbit, okay, low earth orbit, to go against going against the gravitational pull of earth, how much velocity it has to attain? 17,000 miles per hour. Okay, so initial is 0 and final is 17,000 miles per hour. So what is the gap? Del v is equal to how much? 17,000 miles per hour. Understood? So if you want to launch a rocket, this del v must be equal to 17,000 miles per hour, and usually u, this mass of rate of ejection of the fuel, is kept at 4000 meter per second. So this is basically rocket equation. So rocket equation says that how much fuel you must burn. Okay, how much fuel you must burn to attain this del v. That means 17,000 miles per hour. Okay, I will show you an example. Suppose that suppose this from here, if I want to get m, this one del v u, ln means nothing but log e, isn't it? So m initial divided by mmt, isn't it? So m, if I want to get m initial by m mt, it will be equal to how much? This will go as del v by u exponential, or e to power del v by u, m initial by mmt. Okay, so these are the rocket equation. This is basically a rocket equation. It tells you that how much fuel has to be burnt. Okay, what is the ratio between m initial and mmt you must maintain to attain a velocity of del v. For our low earth orbit, it is equal to 17,000 miles.